My name's Hannah. I'm a fourth year natural sciences student at the University of Exeter, and I'm going to tell you a little bit more about my master's project. So what's great about studying here is that I don't have to choose a single science subject, so I get to stay pretty interdisciplinary. So when I studied A-levels, I didn't do biology. However, since studying natural sciences, I've picked up biology, and in fact, my main interests are physics and biology. My two main fields of interest are nanoscience, which is the kind of physicsy stuff, and immunology and cellular biology. So this is the kind of biology stuff. And what's great is I've been able to pick a project that enables me to use both of these. As part of my project, we get to work alongside professors, PhD students, postdocs, and you get to be part of a real research group, which is really, really great. We also get the choice of a project. So I got to choose a project that encompasses all of my favourite parts of science, the title of which is Nanoscale Infrared Biomolecule Spectroscopy, which sounds super complicated. Basically, it's really hard to determine the structure of very small things, so very small molecules. My project is basically to come up with a way of looking at these molecules, determining the structure of them, and finding out something about them on an individual molecule basis. If I introduce infrared spectroscopy a little bit first, so it's a really widely used technique, and it basically identifies the bonds within a sample. So at the moment, you have to use a really big sample to do this with. However, as I said, we want to look at individual molecules. We've kind of come up with a way of doing this, and we use this really cool material called graphene. So you've probably heard of graphene. It's got tons of cool properties, and we use it as a way of exciting these things called plasmons. So plasmons are oscillations that we can form in the surface of the graphene, and it basically acts as a way of us shrinking the light down, so we can make light much smaller. By making the light smaller, we can look at even smaller things, so we can probe individual proteins, which is exactly what we want to be able to do. We've pretty much succeeded in doing this. We've got pretty far. We're not all the way there just yet, but in my year and a half doing my master's project, we've achieved a great deal. Hopefully this is going to be really useful in the future. So for things like designing drugs, when you want to know what their active state looks like and perhaps their inactive state, how their shape might change in our body and if they're perhaps toxic. Also in things like Alzheimer's disease, so you get clustering of proteins, and we want to understand how these proteins cluster together and possibly even halt this kind of thing. So a technique like this to be able to look at individual proteins is super important, and I feel really, really lucky to have been part of it and worked alongside some amazing people and made a real difference.